All right, there's one more set of examples that I want to talk about, and that is when I have a second order system that is underdamped. Okay, so here's our canonical second order system. All right, now, like I said, in general, there's really sort of two types that we encounter. First is overdamped. Overdamped is when the two poles are on the real axis. All right, in this particular case, when I have two real poles, I look at the process shown already, and I treat each of those poles using the process I showed. So I look at this pole as one first order pole, I look at this as one first order pole, and I just go ahead and draw the individual components and sum them. When I have an underdamped situation where my poles are complex, I can still factor them, all right, but how to draw that becomes a lot more difficult, all right? And in that case, what we find is basically because I have two poles, the same basic thing applies. So at low frequencies, what we find is that the magnitude is about 0 dB and the phase is 0 degrees. As we move to high frequency, what we find is the magnitude is falling because we had two poles. It's falling at negative 40 dB. In other words, it's the summation of two poles together, negative 40 dB, negative 40 dB per decade. And the phase has made its way to minus 180. In other words, I've got two poles, each contributing minus 90, so I've got a total phase of minus 180. Okay. Now, the dividing line between high and low frequency becomes omega approximately equal to omega n. So the way I treat this typically is I say, well, I end up looking at it. So if this is log 10 of omega, and this is 20 log 10 of the magnitude, what we say is that up until omega n, my basic idea is I view it as two poles sitting at omega n, and then I need to figure out how to adjust the behavior in here based on zeta. Okay, so remember, for underdamped, we're talking about zeta less than 1. Okay, to really understand that, the simplest thing to do is to say, let's go back to h of j omega, which is so it's omega n squared over, so s squared is j omega squared plus 2 zeta omega n times j omega plus omega n squared. Okay, like that. Now let's evaluate this at omega equal to omega n. Okay, let's find out what happens exactly at that frequency. So I have omega n squared over j omega n squared plus 2 zeta omega n times j omega n plus omega n squared. All right, now so one thing I see is if I take j and square it, so you take the imaginary number and square it, you get minus 1. Okay, so I'm going to have minus omega n squared plus omega n squared is 0. All right, so this guy becomes omega n squared over 2 zeta omega n squared times j. The omega n squareds cancel, and I get minus j times 1 over 2 zeta. All right, now remember, this is a complex number. So if I have a minus j, that means that I have an angle of minus 90 degrees. So h of j omega n, I see that he has an angle that is minus 90 degrees. His magnitude, if I take the log of it, is 20 log 10 of 1 over 2 zeta. Okay. Now, critical thing is that I see from this is as zeta gets smaller, so zeta gets smaller, I see that this value here, 20 log 10, let me write this way, as zeta gets smaller, the magnitude of h of j omega n gets bigger, okay? So let's, as an example, let's zeta equal to a half, okay? 20 log 10 of 1 over 2 times a half. This guy here becomes 1. This looks like it becomes 0 dB. Now let's take a look at what this means. Okay, so here is, all right, here's here's sort of some examples. So what I've done is I've plotted in MATLAB the sort of a basic sort of second order system. All right, and I've done that for a couple of different values of zeta. And I plotted this on a normalized x-axis. So this is 1. Okay, so I've divided all my frequencies by omega n. So this is omega n. This is 10% of omega n. This is 10 times omega n. So notice in each case, for frequencies lower than omega n, I'm basically at 0. Frequencies above it, I've dropped to minus 40 dB. Okay, sort of what I would expect. Notice my phase starts at 0, gets to minus 180. In all cases, no matter what my zeta is, when I'm right at omega n, I'm at minus 90 degrees, just as I would expect. Okay. Now, what I've shown here, so I just evaluated, right? I just evaluated, so what's the magnitude of h of j omega at omega n? And for zeta equal to a half, I said it should be 0. Now let's see what it is, right? Looks like it is 0 dB. If this is exactly equal to omega n, as I've indicated, then that's where it's peaked. Or so the value that it takes at omega n is 0, right? I can see it looks like it's going through 0. Now what I showed here is I circled this guy here. It says looks like he's peaking over here. Okay. What I see is that as our zeta gets smaller and smaller, the peaking near omega n gets bigger and bigger. Right? And the actual peak value here is 20 log 10 of this thing in the notes that I defined as MP. And I did this in the second order notes. Okay. All right, I did this in the second order notes. All right. So in the second order notes, I had 1 over 2 zeta square root of 1 minus zeta squared. This is the actual peak value that occurs at a frequency we define omega p as the peak frequency. In general, what we see is that as zeta decreases, okay, omega p and omega n become increasingly equal to each other, right? I just want to kind of show this, right? So when I'm for zeta equal to 0.5 at omega n, we were equal to 0 dB, and I said it peaked. It looks like somewhere over here, right? At that point, right, omega p and omega n are a little bit different from each other. But as that value gets smaller and smaller on zeta, I see that omega p, the peak frequency, and omega n look like they're pretty much occurring at the same spot. Okay, I sort of see that behavior kind of kicking in. So what I can do is I can use these basic properties to sort of sketch what this guy's going to look like. Okay, so let's go over and let's look at an example. Okay. So let's say I have been given h of s equal to 1,000 squared times s plus 1 over s squared plus 2s plus 1,000 squared. Now, first thing you should do when you look at this is you should ask yourself, you should clearly see, I guess, that there are 2 poles and there's 1, 0. And possibly a constant in front of here, right? This 1,000 squared. First thing you should do is you should ask yourself, what am I looking at? Am I looking at overdamped or underdamped when I see this relationship? it would appear that I'm clearly looking at underdamped, right? If you do your check on this, you'll see you're looking at underdamped, right? So I can see that omega n is 1,000. 2 zeta omega n is apparently equal to 2. So 2 zeta times 1,000 is equal to 2. The 2's cancel. So zeta is 0.001. That is tiny. Okay. So this guy's clearly underdamped. Okay. So that means that in this case, what I have is the combination of underdamped poles, pretty heavily underdamped poles, and a 0. Okay. So again, I could take 20 log of everything and look at the individual pieces, but now I pretty much know that what I need to do is when I'm drawing a Bode plot, I look at the combination or the contribution of each individual pole 0, and I add their effects up. All right, so what I'm going to do is I'm going to do that. So there's 20 log 10 of the magnitude of h of j omega. Okay. And I want a long line for this. Okay. And that is terrible. That's not much better. All right, log 10 of omega is x. Okay, so let's start this guy out. So let's dimension this guy. I'm going to say this is 20, 40, 60, 80, 100, 120. All right, so I'm going large because I know this guy is large. Minus 20, minus 40, minus 60. I'll take it a little farther down to minus 80. Okay. All right, now let's dimension our x-axis here. So I'm going to say minus 1, 0, 1, 2, 3, 4, 5. Okay. Minus 1 represents 10 to the minus 1, right? In other words, the log of 10 to the minus 1 is minus 1. The log of 1 is 0. The log of 10 is 1. The log of 100 is 2. The log of 10 to the third is 3. 10 to the fourth is 4. And 10 to the fifth is 5. Okay? So now let's look at the individual pieces. So zeros we know by this point. So I have a 0 at 1. So that means that the 0 is flat until I get to 1, which is the origin, and then I'm rising at 20 dB every decade. So I'll show him rising 20 dB every decade. Okay, that's the 0. Now the pole is this complex conjugate. So omega n was at 1,000. Okay, so I know that this guy, I'm going to approximate him as flat out to 1,000, and then I'm going to say he's falling at negative 40 dB per decade after that. So he's falling more sharply than the other guy is rising. Okay. Now the other thing is I know that he does a little bit of peaking there around omega n, and I said, you know, the easiest way to look at that is I can look at the magnitude of the transfer function for those underdamped poles at omega n. So I can say magnitude of h of j 1,000 in this case is equal to 20 log 10 of 1 over 2 zeta. All right, so if I plug in that 0.01 and I do those calculations, you should see that that becomes about 53.97 dB. So this guy's shooting way up there, right? So that's somewhere right around, I don't know, about here. So the way I approximate that guy is I say, well, he must do this actually. All right, so he must actually kind of shoot up like that. Now what I do is I sort of sum the combination of these guys. Okay, so at all frequencies, I sum. So out here I have 0 plus 0, so I keep going, 0 plus 0, 0 plus 0. Now I start to rise. I have 0 plus the effect of the 0. All right, so I rise, I rise. Now at some point here I start to rise up more because of the effect of this guy. Now as I get to really high frequencies, remember this guy is plus 20 dB per decade, and this guy is minus 40. So by the time I get to high frequencies, it better be the point where I have minus 40 plus 20 is minus 20. All right, so eventually over here I'm going to be falling at, all right, so let's see, over here at some point I'm going to start falling at 20 dB per decade. Now, because of this effect here at 1,000, this guy jumps way up. It should be, so the 0 is contributing 60 at that point. This guy's contributing 53.97. So if I have 60 plus 53.97 would be 113.97. So this guy would look like this. So 113.97 is about here. This guy's going to rise up and shoot back down and then continue on. Okay, so the total effect, just to make it clear, let me thicken that line up. Sketch it. And then follows it. Okay. Now, angle-wise, it's tricky to draw the angle, right? But what do I know? I know that for the angle, it better start at 0. Around here, it better start to rise up to 90. By the time I get to here, it better be done rising to 90. And then it's going to drop 180 from there, right? So it's going to go from plus 90 down to minus 90. Now, let's look at what MATLAB says. All right, here we go. All right, so we see that at 10 to the 0, or 1, we begin to rise. So I rise at 20 dB per decade. Eventually, I fall at 20 dB per decade. So the black lines there are my asymptotes. And I see that at 1,000, I'm equal to 114 dB. And I said it was 113.97, so it's just a rounding effect. All right. Now, phase-wise, again, start about a factor of 10 before the 0. I begin to rise. I'm at exactly 45 degrees there at the 0. Basically, by a factor of 10 afterwards, I've hit about 90 degrees. And then very rapidly drop down another minus 180 to minus 90 right there. Okay. There's lots of examples you can look at, but hopefully the set of examples in this lecture really will help you to understand how to plot this stuff.